Okay, so my name's David Bowler.
Yeah.
I'm a reader in physics here, so the UK has this system where you start as a lecturer, then a reader, then a professor. So I teach physics in the physics department, but my research is here in the London Centre for Nanotechnology. So my research involves studying surfaces of semiconductors and nanostructures on semiconductor surfaces. Now, in order to understand that, you have to understand that matter is made up of atoms. This is a standard and well-accepted scientific result. Atoms contain electrons, so they have a positively charged centre and they have the electrons around the outside, and the flow of electrons is what gives us electricity. So by using the theories of modern science, we can understand how atoms react to each other and how they interact and the properties. And now those theories are based on quantum mechanics, which has been an accepted theorem since the 1920s when people like Schrödinger worked on it. And in fact, almost all of my research involves solving the Schrödinger equation. Okay, this is a very famous equation that he wrote down. And it's wonderful because it's a very simple equation to write, but it's almost impossible to solve. In order to solve it, we have to use computers. Now, most problems that we encounter in the modern world involve computers. So NASA, when they're wanting to send a space probe, or the ESA, the European Space Agency, use computers to solve the equations of motion of satellites and planets. Okay, so those equations, many of them date back to Newton in the 1600s. Even so, we still can't solve them exactly. We can't write down a formula for the position of a satellite in space. We have to use a computer to predict it forward in time. In the same way, with the quantum mechanics, we have to use computers to predict what the electrons are doing in the system. From the electrons, we can understand how the atoms are joined together. From the atoms, we can understand the properties of the material. Now, a semiconductor like silicon is the basis of modern society. So all electronics uses silicon or related materials. Now, the interesting thing about a semiconductor is, on its own, in its standard form, it does not conduct electricity. But by making small changes to it, you can make it conduct and you can make it switch on and switch off very easily. So what people like Intel do is they take very, very high quality silicon crystals and they add extra atoms to those silicon crystals in order to add electrons into it and enable it to conduct. Once you've done that, you can then put a piece of metal on the top to make a stripe, and when you put a voltage onto the metal, you can either pull electrons in or push the electrons away by changing the voltage, and that will turn on or off the conduction. And that simple switch is the basis of the entirety of modern electronics. That's called a transistor, and it's embedded into every single chip that you have in your phones or your computers. So the channel of a transistor you can think of as being a river. Okay, so you've got water flowing, that would be the electrical current, and by controlling the water flow you can switch something on or off. Now, the point about a transistor is it takes a very small voltage, and that's the voltage you apply to the gate, and it controls the current flow, so it amplifies. You can imagine somebody with a hydraulic dam, maybe, or somebody at a weir who can control the flow of a river by making just a very small change. So a toddler, given the button, could push the button, change the height of the dam and control the flow of a mighty river. Ideally, you wouldn't send a toddler into the control room of a dam, but that's the kind of the picture that we might have of a transistor. So my current research is based around semiconductor surfaces and silicon. So you can see a model of silicon here with a particular reconstruction. A reconstruction is where atoms on a surface rearrange in response to the surface being there. So with silicon, what we're interested in is making individual features on a surface. So there's a company in Texas called Zyvex Labs who actually have something called an STM, a scanning tunneling microscope, that can image and manipulate individual atoms on semiconductor surfaces. And they do something called atomically precise lithography. So they take a silicon surface covered in hydrogen and they bring an STM tip in, and by applying a voltage pulse they can actually remove individual atoms from the surface exactly where they want it. It's taken them 2 or 3 years, but they've now got to the stage where they can control the position of the holes in the surface to better than a nanometer. And a nanometer is 1,000th of a millionth of a meter, or if you prefer, a millionth of a millimeter. And that really is atomic precision. So what we need to do is we need to understand how the hydrogen binds to the surface, how it moves around, because a lot of what they do after they've taken the hydrogen off involves heat. And so if they've made a pattern and then they heat it up and the hydrogen moves, the pattern disappears. So we've actually spent a lot of time working on this, thinking about what materials they can deposit in the holes they've made and how they can control that. Now the computer modelling we do, the standard approaches involves a computer effort that increases with the cube of the number of atoms in the system. So the more atoms you have, the harder it is, and if you double the system size, of course the cube of that means it's 8 times harder. 10 times the system size is 1,000 times harder. More interestingly, if the government gives you a computer 1,000 times bigger, you're going to do 10 times as many atoms. And accountants and government ministers tend to like you to use things efficiently, so you want to be able to do better than that. And we can, so I'm one of a team who's developed the code Conquest, which allows us to scale linearly with system size, which means that if you have a computer 1,000 times bigger, we can do 1,000 times as many atoms as we did before. And using that, we've solved the electronic structure, we've solved the quantum mechanics of systems with over 2 million atoms. There's a new computer in Japan which will be online in a few years' time, as well as in other countries, where we will have what's called exascale computing, which means 10 to the 18 operations per second, which is a billion operations per second. At the moment, we only have 10 to the 16 operations, so that's 100 times smaller. And we're hoping that we'll be able to apply these techniques to all sorts of different areas, including biochemistry and medicine, semiconductors, understanding geochemistry, all sorts of other areas. So the aim of our simulations is, well, at one point it's basic science. We want to understand how semiconductors work. By developing this new technique, the Conquest code, we want to be able to solve systems which are larger and larger and therefore more and more realistic. One of the areas that we're currently working on is using semiconductor nanowires in place of the standard transistors that Intel are using, in place of the channel of a transistor. Now, in transistors, in semiconductor circuits, there's a huge amount of work which is done. There are various huge fabrication facilities. They take wafers which are up to about 12 inches, so a foot across, and they pattern them. So they cover them in a resist and a chemical, then they remove the resist with light, and then etch away and add metal, and that makes the semiconductor gates. Now, the company I was talking about, Xivex Labs, do this on the atomic scale with a single STM tip. By growing semiconductor nanowires, then we might actually be able to do that in a rather more efficient way. So as the nanowires, they're very beautiful. If you put down tiny gold dots, maybe a few tens of nanometers across, remember a nanometer is a millionth of a millimeter, and then you introduce, say, silicon vapor or germanium vapor, these nanowires will just grow spontaneously. And you can control the growth, so you can control the radius, the size of them. You can also coat them in a different semiconductor, which gives them very, very interesting properties. By doing that, by growing these nanowires, we could then put them down on the surface of a semiconductor and use them as the channel, so that's the river, if you like, of the transistors. And because we can grow them and we can control the doping, we can control their properties with exquisite precision. However, to do that, we have to be able to understand what their properties might be, and that's where my modelling comes in, because we can take the nanowire, we can actually build them physically in a computer, add in different atoms, say boron or arsenic or phosphorus, to change the conduction properties, and also particularly see what happens when you put those elements in different parts of the nanowire. So if you have a silicon center and a germanium outside, and you put the dopants into the germanium, do you get very good conduction in the silicon? That's the kind of question we might ask. That can then have effects on the heat loss in chips, which actually is one of the major problems facing semiconductor manufacturers, is how to get rid of the heat. They have to build the chip so the heat can be radiated. And if you look at the more technical websites, they tend to discuss things like the voltage that's used in transistors and the power that's dissipated. And a lot of the time that's the problem, it's just getting the heat out. Because if you heat it up, atoms start to move, because temperature is just equivalent to motion on the atomic level. And once atoms start to move, then all of the careful patterning that you've done can start to break down, your transistors start to fail, your phone fails, and you have to go buy new.